Welcome to the topic of types of solar cells. The topics we'll be discussing in the types of solar cells include monocrystalline, the sizes of cells, prices, polycrystalline, thin film, gallium arsenide, dye-sensitized, organic, perovskite, multi-junction, bifacial, heterojunction with intrinsic thin layer, back contact, ribbon silicon, tandem, concentrated, quantum dot, plasmonic, biogenic, transparent, flexible, nanowire, hybrid, printable, hot carrier, tandem, perovskite, graphene, carbon nanotubes, PERC. So we'll start off with monocrystalline. Monocrystalline silicon cells are made from a single crystal. They are more efficient than polycrystalline. In the years past, they used to be around 30% more expensive than polycrystalline, but in the year 2023, these days, the prices of mono and poly are almost the same. In some cases, the new mono are actually cheaper. The reason for this is that they're being produced in more quantities than the poly. They are also easily recognizable by their dark color. Mono is usually a darker color, almost like black, and polycrystalline is more blue. And you can also see in polycrystalline, you can see differences in the color. In mono, the color will be all the same color with no patches or splotches. So that is the basic difference in the looks of the mono and poly. There is also a thin film. It is like a single color, usually brown, and it used to be cheaper than poly and mono, but due to the lack of manufacturing, it has become more expensive than mono or poly. Basically, the mono will look more like a black color. The Czochralski process, abbreviated CZ, is used to create the ingots which are used to make monocrystalline solar cells. These ingots look like this when they're pulled out. Basically, you have a small seed crystal, and this is the ingot itself, and this is liquid silicon inside a quartz crucible and surrounded by a graphite. So you have a quartz crucible with solid metal grade silicon inside, and when they pull it out with the seed crystal, so what ends up is at least 95.999% pure silicon, which is this ingot, and it can be up to 6 to 8 nines depending on the requirement. For solar modules, it is, or solar cells, it is around 5 nines, but for semiconductors, it is around 6 to 8 nines. So that is how these pure silicon ingots are created for monocrystalline solar cells. Now we come to the cell sizes. The earlier numbers like M2, M4, M6, these are the older versions. Usually they were smaller. Nowadays, the manufacturing has gone towards larger sizes. So M12 and G12 is the same size. The length is, it's a square solar cell, and the length is one of the sides, and the diameter is diagonal across. The diameter is the diameter of the ingot that is required to make this solar cell. So basically, it is what's important is actually the length. So it's length, and then if you square the length, you will get the area, unless the corners are cut. Anyway, so the M12 P-type wafer was introduced in 2019, and the G12 was initially named M12. It's the same size and same specifications. It has a larger area, and the objective of making these larger is that it reduces LCOE, which is, LCOE stands for levelized cost of energy. That means over a long term, what will the electricity cost? So it is around a few cents per kilowatt hour for solar cells at an industrial scale. But LCOE is usually used in industry sizes, like for example, like industrial scale installations, which is like gigawatts. Hundreds of megawatts to gigawatts. This is an image of M12 compared to the M6. Now we come to the prices. There is two types of mono cells. One is P-type and N-type. N-type has a longer life and usually were more expensive. But now you can see that in August 2023, these days, the prices are, for example, 3.05 renminbi for N-type, M10 size, and 2.95. So the difference is only like 10.1 renminbi between 3.05 and 2.95. That's around 3% of a difference. That's hardly a difference. So when you take these cells and you put them into a solar module, the difference might be just 1 or 2% in the final production price. And in the near future, that means within a few months to a year or so, you might see that in the market, the N-type modules might be cheaper than the P-type modules, even though they're better, just because of mass production. So here are the prices also for reference. Polycrystalline solar cells. These are made up of multiple crystal structures. They're less efficient, but used to be more cost effective. They have the blue color as mentioned. But nowadays, almost all of the new ones, which are mono, are actually very close in cost to the poly. So it's the only poly that you might find at a lower rate than mono are the old ones, if somebody has any stock left over. P and N types. There are two types of monotype cells. One is the P-type and one is the N-type. The P-type has a silicon base with boron atoms to create the overall positive charge. So the N-type are basically the opposite of the P-type. They have a silicon base infused with phosphorus charge, and the N-type uses phosphorus atoms to create the negative charge. The first solar cells that were created were N-type, and they were designed to be used in space, but they were around, I think, $2,500 per watt, and prices have come down to pretty low rates, like a few cents per watt nowadays. So then commercial production of P-type was more dominated, but now in the future you will see that N-type is gaining more mass production. So you might actually see that in some time from now, maybe within a year or so, the N-type will actually beat the P-type in prices, just like the mono beat the poly in prices because of mass production. Currently the P-type are common, but the N-type are growing faster. And over the last 40 years, the P-type are the ones that have been having the market share. But in the future, you can expect the N-type to have market share. The reason is basically reliability and long-term capability of production. Combined, basically, I mean production of energy. Now, the thing is, if you use the boron to create the P-type, what happens is when it gets exposed to light, it has more light-induced degradation. And this reduces the capability of the cell over the long run compared to N-type. N-type has less degradation, and N-type also have higher temperature tolerance. So they have longer life, they have higher efficiency. They are currently just 3% more expensive to produce. One of the largest manufacturers, Jinko, has a Tiger brand module, and this uses, they're focusing on the technology they're focusing on is multi-bus bar, tiling ribbon, half cut with high efficiency. There are four sub-series in the Tiger modules. They include P-type and N-type type cells in these modules. The difference we mentioned is the N-type uses a doping to create a negative type substrate, and the P-type uses boron to create a positive charged substrate. This is a diagram of what the P-type and N-type layers look like. So the degradation rates for the P-type is 2% for the first year and then 0.55% for the next every year after that, all the way up to the 25-year warranty. So you can expect the power output to be at least 84.8% at the end of 25 years. For the N-type, the degradation for the first year is 1%, and every year after that it is 0.4%, and the warranty is up to 30 years, and you can expect 87.4% at the end of 30 years at least. The graph shows the benefit of N-type when it comes to long-term guarantees and energy production. So you notice that the red-colored P-type will degrade faster, and the warranty is for 25 years, and the N-type has a warranty of up to 30 years. Basically, the warranties are guaranteeing anything above 80%. So you can have a 25-year warranty for the P-type, and you can have a 30-year warranty for the N-type. And if the cost nowadays is almost similar, so obviously you should be selecting the N-type if you can get it at a similar price. So as I mentioned, the price difference, the production price right now for the cells are available with a 3% price difference. So you can expect the production price to be within 1% after the module is created. Now what happens after the supply chain? We expected in the next few months the N-type modules that are available would be lower cost than the P-type older modules, which are of an older batch. So I've summarized the selection for most applications, which are like general applications related to residential or factory type applications. The double glass is more reliable than having a plastic EVA backsheet. The N-type is better since the prices are similar now. Mono has already become cheaper than poly for all the new modules. And the largest failure rates currently these years are for the junction box. So make sure that the junction box is of good quality. Currently in the year 2023, the top two manufacturers which are consistently performing well in the reliability area are Jinko and Trina. These are the top two. They are one of the largest suppliers also. And I think Jinko would generally win on price because they're able to optimize the whole production process and the supply chain. By supply chain, I mean shipping and dealing with their partners in different countries. At least that is my experience in Karachi. So I think Jinko offers the best prices. Not that I'm an agent for them, but I'm just informing you that just because you might be getting the best, even if you're getting the best prices for Jinko and Trina and the others are more expensive, you should know that they are the best performing in consistent reliability testing. And for specific cases and locations, it is better to ask for an expert opinion, because this is generally for residential and factory applications. These are the things that I mentioned. Now we come to thin film solar cells. Thin film uses a thin layer of semiconductor material to convert the sunlight into electricity. They're different from silicon solar cells because solar cells are thicker, they're more rigid, and they're in like sort of like separate cells. And thin film is more like one layer over the whole glass sheet of the whole solar module. The advantage of thin film used to be lower cost, but since they haven't been being made, now poly and mono have already beaten thin film, and I don't think any of the currently thin film is more expensive. In the market at least, thin film is more expensive than poly and mono. Amorphous silicon is a non-crystalline form of silicon that is deposited as a thin layer. So amorphous silicon solar cells are a subset of thin films solar cells. It is because of the ease of manufacturing, and it's easy to deposit, and it's lower cost. So it was easy to manufacture, but it did used to degrade less. So basically it would degrade below within 80% within 10 years. It had something like double or triple the degradation rates of polysilicon. And this was popular from the 70s to the 2000s for small things like calculators. You would see these like chocolate colored cells in these devices. Cadmium telluride was also a popular material which gained attention for making solar cells because it was lower cost to create thin films. But when it came to mass production, the Chinese selected poly and mono. So because of that, it's not so popular nowadays. But it was considered as one of the candidates for creating low-cost solar cells for at least 10 years. Okay. The advantage of cadmium telluride is that it is semi-transparent. So you can sort of use it in areas where you have dark glass and you have some light coming through. Copper indium gallium selenide, CIGS. This is a thin film technology which has the advantage of high efficiency and also flexibility. The manufacturers these days, they use this to create flexible solar panels because it can be deposited using sputtering and co-evaporation. Organic photovoltaic cells, OPV. They use organic carbon-based materials for their active layers. They're highly flexible, can be fabricated on plastic substrates. However, currently the efficiency is low. Gallium arsenide. These are one of the oldest initial solar cells and still used currently because they have extreme efficiency and excellent performance. And they're usually used in space applications, and they're used for powering satellites, space probes, and other spacecraft where cost is not an issue. And I think when they started, it was around $2,500 per watt. They might be a lot lower now, but they're used for very specific applications. The advantages are high efficiency because gallium arsenide absorbs sunlight across a large range of wavelengths compared to poly and mono. The other thing is gallium arsenide solar cells are more radiation resistant. So when you're using them in space environments where there's a lot of ionizing radiation, this is important for their capability to survive in space and the harsh conditions of space. Another advantage is since they're highly efficient, the gallium arsenide solar cells are much lighter compared to all other technologies. They're also used for astronomical observatories like the Hubble Space Telescope. Dye-sensitized solar cells, also known as Grätzel cells. This is also a thin film type solar cell which mimics the photosynthesis in plants. They were first introduced by Michael Grätzel and Brian O'Regan in the 1990s. They have gained attention as a potential alternative to silicon cells because of their lower cost of production, their flexibility, and their lightweight applications. Here is a diagram of a dye-sensitized solar cell. Dye-sensitized solar cells work by having a titanium dioxide layer coated with a photosensitive dye. Usually it's titanium dioxide. The dye absorbs the photons and moves excited electrons from the dye molecule to the semiconductor material. The photoelectrode is immersed in an electrolyte, which is used as a medium to transport the electrons from the semiconductor material to the other electrode. The electrolyte usually is a liquid containing ions that can easily accept and transport electrons. There is a counter electrode that is usually made out of a conductive material like platinum, which catalyzes the reaction and is responsible for the reduction of the electrolyte's oxidized species. The circuit is completed by having the excited electrons move from the photoelectrode to the counter electrode through an external circuit. This actually generates the current. The advantages of dye-sensitized solar cells include cost effectiveness. This is due to less expensive materials and simpler production processes, and flexibility because they can be manufactured on flexible substrates, which allows them to be used as flexible solar panels on curved surfaces and wearable devices. Dye-sensitized solar cells have the advantage of being partially transparent. This allows them to be integrated into windows and building materials. They also have good low light performance, so even in indirect sunlight or low sunlight, they can still be used to generate energy. Here is an image of dye-sensitized solar cells integrated into a building. This building is the Swiss Tech Convention Center. The challenges for dye-sensitized solar cells include efficiency. They have a very low efficiency compared to traditional solar cells. The other challenges include electrolyte choice, which has a complete impact on the overall cell performance, and being able to scale up production while maintaining the quality required. Organic solar cells use organic materials as the active layer to convert sunlight into electricity. The silicon-based solar cells use inorganic semiconductors to convert light into electricity. Organic solar cells have two layers. One is called the donor layer and the other one is the acceptor layer. The donor layer contains a material that can efficiently absorb the photons and generate electron-hole pairs, also called excitons. Exciton splitting is the process where, when photons are absorbed, the excitons are created. These excitons need to be split into free electrons and holes before they can recombine. This process usually occurs at the donor-acceptor interface, where these excitons need to be split into free electrons and holes before they recombine. The energy level offsets at the donor-acceptor interface facilitate the electron transfer from the donor to the acceptor. Charge collection is the process where the separated electrons and holes migrate through the respective donor and acceptor materials toward the respective electrodes, which is the anode and the cathode, generating. The separated electrons and holes migrate to the respective donor and acceptor materials, and inside those materials you have the electrodes, which is the anode and the cathode, through which the electrical current is generated. This process is called charge collection. Organic solar cells have the advantage of lightweight and flexibility. They can be processed into creating flexible thin films. Due to the simpler printing processes required to make organic solar cells, they can avoid the more complex manufacturing processes required for silicon-based cells, and therefore the cost of fabrication could be lower. Another advantage of organic solar cells is tunable absorption. This is where you select different materials so you can absorb different wavelengths to generate the electricity, and the different wavelengths selected are based on the kind of ambient light available and the kind of lighting conditions you're going to use a solar cell in. Another advantage of organic solar cells is color variety. By modifying the materials, you can change the transparent color of these cells, and you can match them to the aesthetics required. The challenges for organic solar cells are efficiency. Compared to silicon solar cells, the efficiency is lower, so people are working on that. Stability. The other challenge is stability. Just like dye sensitized, they're sensitive to moisture and oxygen and UV radiation, which causes faster degradation. Due to the faster degradation, the lifespan of organic solar cells is less compared to silicon-based cells. Another challenge is that developing efficient organic materials and optimizing the donor-acceptor interfaces requires a lot of design and material engineering. Perovskite solar cells are becoming more popular because of their low cost and high efficiency. Their name perovskite is based on the crystal structure that they utilize, which is a particular arrangement of atoms that can be found in certain minerals. Perovskite solar cells use a thin film of perovskite material as the light absorbing layer. Usually, the structure is a metal cation, an organic molecule, and a halide anion. This composition allows perovskite materials to efficiently absorb sunlight across a large spectrum of different wavelengths. When sunlight hits the perovskite layer, it excites electrons into electron hole pairs, just like the organic cells. Then we have charge separation, just like the organic cells. Then the electric circuit is the one that actually uses the energy. The reason perovskite solar cells are gaining attention these days is because of their high efficiency as compared to traditional silicon solar cells. Also, perovskite solar cells can be produced at a lower cost because they can be spin coated or inkjet printed, and this can potentially be less expensive than the traditional solar cells. Another advantage of perovskite solar cells is the tunability aspect, where you can adjust the chemical structure and optimize for different types of wavelength absorption. This is an image of a perovskite solar cell made by Nanjing University. The challenges of perovskite solar cells are stability. As compared to silicon cells, their degradation rate currently is much more than silicon solar cells. Another challenge for perovskite cells is toxicity. Some of the perovskite materials being used contain lead, which can raise environmental and health concerns. Challenges include being able to scale up perovskite cells production while maintaining quality and performance. And the main thing is durability compared to silicon-based cells, which are already available. Multi-junction solar cells and tandem solar cells are very similar terms. I'll try to separate them also. They are advanced photovoltaic devices which consist of multiple semiconductor layers stacked one on top of each other to increase the spectrum of sunlight that is absorbed and therefore increase the efficiency. Since mono and poly and thin film cells usually are single junction cells, they have a limit on the kind of absorption they can do. Here is an example of a multi-junction solar cell. You've got 3 different layers. Here is an example of a multi-junction cell made up of 3 different layers. The electrical contacts are only at the top and the bottom, and there are 3 different layers with 2 different junctions. Multi-junction solar cells work by having different band gap energies which determine the wavelengths that the light each layer shall absorb effectively. Each layer is engineered to specifically capture a specific portion of the solar spectrum. This allows a wider range of wavelengths to be absorbed compared to a single junction cell. The advantage of making a multi-junction solar cell is that you can increase the efficiency beyond the theoretical efficiency of a single junction cell. By capturing a larger portion of the spectrum, they can generate more electricity in the same amount of light. The multi-junction cells have a tandem structure where different layers are stacked one on top of each other. Usually the higher bandgap energies are placed on the top and the lower bandgap energies are placed lower from the incident light. By stacking it this way, it ensures that the higher bandgap energies are absorbed first and they are not absorbed by the layers below it, and allows for the maximum efficiency possible. By placing the higher bandgap energies on top, it makes sure that they are not absorbed by any layer below it, which is generating less energy than the highest energy layers. To make sure that the multi-junction solar cell is efficient, it is important that the amount of current generated by each layer be very close to the amount of current generated by the other layers. This balancing of the amount of current created by each layer can be done by changing the properties of the layer and the thickness of the layer. Since multi-junction solar cells can provide higher efficiencies than single-junction cells, that is the reason they are used in space-based applications where weight and space are a main issue. The higher costs of creating multi-junction cells is justified by the need for maximum power in space and weight-constrained environments. Here is an example of a multi-junction solar cell. The challenges of multi-junction solar cells include complexity in the design and fabrication of these cells, because they need precise layer engineering and alignment between the layers, and this increases the cost, which is higher because the manufacturing processes require specialized materials and also are very complex. Bifacial solar cells are a type of solar cell that can generate electricity from both the front and back sides of the solar cell. These bifacial solar cells convert the sunlight that is directly striking on their front surface, and also they can capture and convert the sunlight that is reflected off the surfaces behind the panel. Bifacial solar cells have the advantage of larger amounts of energy generation by the same solar module. The way bifacial solar cells work is by having a transparent or lightly textured back surface, which allows some of the light to pass through and reach the rear-facing semiconductor material. This allows production of energy from both sides. The ability to use reflected light to contribute to the overall energy output is called a reflection gain.